Ja, haha, da sind wir ja. So, nach den Schauspielern und ganz viel Science Fiction kommen wir jetzt zu Science ohne Fiction. Die ESA wird sich gleich hier auf der Bühne einfinden, in Form von zwei Personen, die euch sehr, sehr, sehr viel über den Weltraum noch zu sagen haben. Ich möchte mich an dieser Stelle schon mal für heute verabschieden. Ich werde also nachher am Ende der Show nicht mehr da sein. Es kommt im Anschluss dann nochmal die Premierenfolge von The Boys, also im Anschluss an die ESA. Das heißt, ihr könnt dann auch hier bleiben und euch das noch ein bisschen reinziehen. Die beiden werden einfach so lange machen, wie sie wollen und wie ihr Fragen habt. Für die Fragen bitte dasselbe Prozedere wie immer. Dieses Mikro hier in der Mitte ist dafür gedacht, dass die Fragen hineingesprochen werden. Fragen, die einfach so in den Raum geworfen werden, funktionieren nicht, weil ihr wisst ja, im All gibt es keinen Schall. Ergo nur über das Mikro und die beiden werden euch dann schon gleich sagen, wann denn Fragen gestellt werden sollen und dürfen. Aber jetzt begrüßen wir erstmal auf der Bühne Thomas und Cassie von der ESA.
So, hello everybody, and welcome to the last panel of the day here. Thank you so much, all of you, for showing up. It's
yeah, great turnout.
Great turnout for 7 o'clock. I would have gone for dinner, but
on a Sunday evening.
So no, it's great to have you here, and thank you for coming. We think that the topic we're talking about today is really, really important. We're going to come down from Mars and all of the other exciting things that maybe you've seen from us or seen at our stand. And we're going to come back down to Earth. As we've said in the title of the presentation, our spaceship Earth. We're right now in the best spaceship that's ever been, our planet. And unfortunately, as you'll learn over the next few minutes, and as you might know already, our planet's not in the best way at the moment. But we want to show you what we can do from space. We want to show you what the missions of the European Space Agency are doing to try and bring facts and data to what's happening to our planet. So it might be a bit of a tough ride, but
it'll be all right.
Yeah, but we hope you'll find it very interesting, and we hope you'll go away with a bit more knowledge about the spaceship that we're flying on and that we need to look after. But I'm just a spaceship driver. I fly Earth observation missions for the European Space Agency. My job is keeping them in orbit, dodging space debris, and making this data. But the real interesting stuff comes from our scientists, and we've got Cassie Sturman today.
Wait. Sorry, if you're flying the robots, who's flying the planet?
Yeah, well, I think we should be, but we're asleep at the wheel. So it's my pleasure to welcome Cassie here, who's going to talk to you for the next 40 minutes or so about what we can see, and then we'll come up at the end, and if you've got any questions about what it's like to fly the things, I'm here. And all the proper science questions I can hand over to Cassie. So enjoy, everybody.
Yeah, thank you very much, Tom.
Good stuff.
All right, so here goes. As Thomas mentioned, my name is Cassie Sturman. I'm an Earth and planetary scientist. And this is my first time ever having the chance to speak about climate change. This is the first time I've ever been asked to speak about the state of our planet as it is right now. What is the story of our planet from space? And what are the projections for our planet's future? I feel like there's a lot of momentum for this topic in a way that there hasn't been in the past. And I'm going to take you on a journey starting from Mars and Venus and these other planets in our solar system where we've been spending so much of our energy this weekend so far. And then I'm going to kind of narrow in on Earth and what the story is for our own spaceship right now. So the first piece of telemetry I wanted to show you, and raise your hand if you know what I mean when I say telemetry. Several of you, lots of you. Okay, awesome. So in science fiction, people talk about incoming telemetry all the time. And all it means is that there's data coming from somewhere far away. You might hear me sometimes say remote sensing data. You might hear me sometimes say telemetry. It's the same thing. It just means that we have scientific instruments from somewhere far away or looking somewhere far away, sending data back to us at our home on Earth, okay? So what we're looking at in this image is an area in northwestern Siberia. This is an image taken by the Sentinel-2 orbiter of the ESA Copernicus fleet. And can anyone here tell me, for a calendar, where are the calendars at, Thomas? I'm pretty sure I left you responsible for those.
The calendars are right behind you.
Ah, okay,
Yeah,
so for
we've got presents.
for a calendar, can anyone tell me what kind of geography we're looking at here in northwestern Siberia? What are we looking at? Tundra, okay. You deserve a calendar for trying. Anyone else? Can you be more specific? Who said permafrost? Come up here, get your calendar. And Tundra, you're coming up here as well for being the first person to answer a question. I mean, you're not wrong. Yeah, so this is permafrost. We're looking at permafrost here. And you know, because there's this vast network of small ponds. So you're looking at melt ponds as the permafrost is melting across the Arctic. You see these meandering streams, these slow-moving, sediment-filled streams as the permafrost from higher elevation melts and that water is transported to lower elevations. We see these bright, beautiful melt ponds, and this is just one little slice of what's happening on Earth right now. But again, before I get into too much detail, I'm going to take you on a tour of the solar system. And the reason I do this is because this is kind of my own journey as a planetary scientist. I'm new to Earth, okay? My background is in radar science. And you use radar science to study basically all of the planets and all of the moons. My background is on Mars, but I've also done work on like Venus and Titan. I've looked into Europa data. Here's a selection of different telemetry, so remote sensing missions around different planets. In the top left, we have Mars Express. It's an ESA mission. It's been there, I think, since 2002, 2003. Venus Express in the top center. We have the upcoming JUICE mission to the Jovian moons in the upper right. There's ExoMars coming up, a rover. Rovers are also a kind of remote sensing. This one exploring the ground on Mars in only a couple years. There's this little image here of the Sentinel fleet. I'm going to get into a bit more detail later on what exactly that is. And finally, this is the only non-ESA mission on the slide, but I think a lot of you might be excited about it. This was New Horizons from a couple years ago, passing by Pluto. All of these are different kinds of telemetry. And okay, here is one of the first pieces of telemetry I ever studied. Does anyone know what kind of data this is? I mentioned what kind of scientist I am a second ago. Radiation, it's a kind of electromagnetic radiation. Sorry? It is, yes, come up here, you're getting a calendar. They're wonderful calendars, they got amazing, amazing Earth observation imagery. That's right, so this is actually a radar image of a glacier on Mars. And if any one of you have spent more than like 5 minutes alone at a room with me, I've probably started talking to you about Martian glaciers. Here's a couple pictures of different glaciers that we see on Mars. These are mountains, and then you see these kind of blobs surrounding each of the mountains. This is a bird's eye view, by the way, so imagine looking at mountains from above. We see these blobs surrounding all the different mountains. Those are clean glacial ice. Here's an image of one of the Martian polar caps from the side. This is real data used to create a 3D reconstruction, another beautiful example of telemetry from another planet. This, well, I showed you what some permafrost on Earth looks like in certain instances. This is an example of permafrost on Mars. So this big image in the center here is from Utopia Planitia, a phrase that might have some significance to like the super Trekkies out there. But it's also a region on Mars, and it was the focus of a lot of my research a couple years ago. And in the bottom left there, we see an example of permafrost on Earth in the dry valleys of Antarctica. Remarkably similar, aren't they? Two more beautiful examples of telemetry. So here's Venus Express, and I'm not going to get too much into detail on Venus, but I thought I would share like my favorite fun fact that came out of these missions. We know from Venus Express that there are regions in the Venusian atmosphere, not on the ground of Venus, but like different levels and layers within the atmosphere that have similar pressures and temperatures to what we see on Earth. So some astrobiologists suggest, like, hey, like, maybe this could be an analog for an habitable environment on Earth. And I'm like, okay, cool. Like, what about the chemical analog, though? But from a pressure temperature perspective, it's really cool. This is another outcome of our telemetry around the solar system. And finally, a very recent result. This came out, I think, in the past couple months. It's been suggested, based on gravity data around Pluto, that there could be water, liquid water, in the subsurface. They hypothesized that there could be gases trapped in a layer right above a liquid water ocean that could be preserved up to 1 billion years based on those gases which act as an insulator. So there's a lot of really cool things happening across the solar system all the time. More examples of telemetry. So I am a huge, huge fan of The Expanse. And I think a lot of us at ESA are, because it is an example of harder science fiction. And when you're a scientist and you see fiction get the science right, it's just inordinately exciting to me. And on top of that, being like a radar scientist, being a kind of instrument scientist, I get over the moon excited anytime radar is mentioned in pretty much any context. And the books, and also the show, but especially the books, talk a lot about the remote sensing capabilities of the different ships. Who here has heard them talk about fast movers? Either in the books or in the show. Like, what they're talking about when they say fast movers are what they see on their radar. They're using a pulse Doppler radar. And one of the limitations of the physics there is that if you're doing this kind of continuous wave radar survey, you can get the position and you can get the velocity of this thing, but you can't get the shape. So they're not saying, I see a missile, they're saying, I see something here moving fast. And the fact that this physical limitation of a remote sensing capability is built into the jargon of the science fiction series I love just gets me over the moon excited. And in Star Trek, so this is obviously not an image from Star Trek, but people talk a lot in the show about like life signs or biosignatures. And for this talk, specifically, I actually looked on Memory Alpha, like how do they explain this science? Because I don't really understand. We all kind of take it for granted. And in the show, it doesn't really make much sense. They talk about like the electrical signatures of specific life forms unique to that body, and I'm like, no. But exobiologists sometimes talk about biosignatures. So James Webb Space Telescope, which is imaged here, and will be launching in the next couple of years, it will be able to see the atmospheres of planets around other star systems, right? It's going to use spectroscopy, a kind of remote sensing, to tell us the composition of the atmosphere of other planets. And by looking at these atmospheres, we can learn something about the relative proportions of methane and of oxygen, and that can tell us something about the likelihood of life existing on that planet, a kind of biosignature, light years away from us. So I find that inordinately exciting. There's parallels with Star Trek there, not exactly the same, but these are more examples of our remote sensing capabilities as a species. So why do I tell you about all these things? Like, why am I taking you on this big tour of the solar system? Well, as a planetary scientist, right, it was a lot more fun to tell people at parties I was studying Mars than telling people I'm a climate scientist. You know, when I tell you there's glaciers on Mars, people are like, oh, cool, you know? When I tell you there's ice sublimating on Mars, people are like, that's great, Cassie, super interesting. When I tell you there's permafrost melting on Earth, when I tell you there's glaciers receding on Earth, people have a very, very different reaction. And I'm going to kind of walk you through now what the remote sensing data from Earth is saying to us, starting with this blue marble here. This is a mosaic from 2011 out of NASA, which is why you're kind of seeing North and Central America through there. And every time I look at a blue marble image like this, I just feel like we're so fragile, right? Massive planet, tiny atmosphere, floating through space, and this is the inspiration for the title of this talk. Since I'm representing ESA, I'd be remiss to not walk you through all the different Sentinel missions. So you've been watching us wear these like different blue-colored Sentinel shirts all week, and I've had so many people ask me, what's Sentinel? What's that? I didn't know you worked there. I'm like, it's not a company. So, the Sentinels are a fleet of different missions under the program Copernicus, each of them taking different measurements from our Earth. Okay, I'm going to walk you through them really quickly. Sentinel-1, that's my baby. That's the radar instrument. Sentinel-2 is an optical imager. It's like a camera, like you have on your phone. Sentinel-3 is measuring the oceans, presumably using spectroscopy. I can't remember, I always mix these up. Sentinel-4 is another spectrometer operating in the visible and UV parts of the spectrum. Sentinel-5P and 5, so 5P is launched, 5P not launched yet. They're operating in like UV and near IR. And Sentinel-6, I think that one's the radar altimeter. I always mix it up with the other one. It is the radar altimeter. Again, measuring our oceans and sea level rise, okay? Now you know, going forward, now all of us will remember for the rest of the talk. There's a quiz later. Okay, beautiful. So now we finally get to see some Earth observation imagery. This is a Sentinel-2 mosaic, and can anyone tell me what it is? What are we looking at? Okay, what coral reef? It is the Great Barrier Reef. Come on up. Come on up. Yes, we're looking at the Great Barrier Reef. It's beautiful imagery. But unfortunately, when we look a bit closer, so we're going to be zooming in on this white box in the upper left there. What we find is that over the course of 1 year, only 1 year, from 2016 to 2017, huge swaths of the Great Barrier Reef had bleached. They've gone white, areas that were kind of dark green. I know this is like low res, but the point of those images is the color. Okay, so look how it's gone from this kind of dark bluish green to this very light whitish blue. This means we've gone from a very habitable, lively coral environment to something bleached and dead and no longer habitable by most forms of marine life, at least not in the same way it was before. Here we have, this is a video representing our measurements of the ozone layer. So some of you might remember the Montreal Protocol in the 80s, where we decided we weren't going to use chlorofluorocarbons anymore. These are chemicals that we use in refrigerants and aerosols that are disastrous for our ozone layer. And what we see is that in late 2018, the ozone layer has started to become a concern again. Okay, the hole is opening up again. People are using these chemicals that just like eat up the ozone layer. And as it rotates around, it starts to spiral. Certain arms of it are creeping up to parts of South America and Australia. And the ozone layer is hugely important to protect us from UV radiation. It's hugely important to keep us from getting skin cancer every time we go outside. And it's critically important that we maintain the integrity of the ozone layer moving forward. And again, this is just an example of what we see when we look at our Earth observation data from space. Here's a Sentinel-2 and I believe Landsat time-lapse looking at deforestation in Bolivia. As you can see, huge swaths are being deforested over the course of like 20 years without being replanted. This is a lake in Chile. Some of you might know that there has been a severe drought affecting huge swaths of Chile since like 2007, 2008. And in 2011, this particular lake, which is several kilometers wide, started to dry up. And moving from like 2018 into 2019, it's dried up completely. People do not expect that it will be bouncing back. It's due to some combination of like climate change causing droughts and development around the area, draining from the aquifer at rates higher than it could be replenished. Classic image when talking about Earth observation and climate change, we have the glacial retreat. These images are very striking from the ground, but you can also see them from space. This is Columbia Glacier in Alaska, going from 1984 to 2016. You can see the fjord has completely emptied along the main channel and even along the tributaries has begun to recede even further. So, taking a break for a second. I need some water from the climate data. Okay, so who here has done a Fourier transform in the past? Some engineers, some mathematicians in the audience. You don't seem very excited about it. He's a very famous mathematician, but something he's not as well known for are his contributions to our knowledge of the greenhouse effect. Fourier was the first person somewhere in the 1800s to describe the temperature of Earth from a mathematical perspective. And this guy was really into cycles. He was really into sine waves. And he would measure the temperature from his location, from day to night, from month to month, season to season, and year to year. And what he concluded was that the temperature of the Earth was much warmer and had way lower variations than what you would expect based on solar radiation alone. And he was absolutely right. Like, we know now that the atmosphere provides an insulating layer to our planet. I mean, if we compare Earth to Mercury, where in the daylight it's hundreds of degrees Celsius, and in the nighttime it's minus 100 degrees Celsius. It has no atmosphere to protect it, really, so it suffers those extreme temperature variations. On Earth, we don't have that. The system is buffered. And Fourier was the first person to suggest that the atmosphere could be protecting us from these drastic temperature variations. A few decades later, we had Eunice Newton-Foote. So she was never photographed or painted, but she's credited with being the first scientist to ever suggest that changing the proportion of carbon dioxide in our atmosphere could change the temperature of our planet. She never got to present her work. Her work was largely credited to other scientists, but it's emerged after her death that she made these major contributions to science. And the point here, I mean, in part to give us a break from looking at Earth images, is to state that the greenhouse effect has been uncontroversial science for hundreds of years now. We've known about it for a very long time. Fourier had no political motive to suggest that the atmosphere protects our planet. Foote had no reason to say that carbon dioxide is going to be a harmful pollutant down the line. This is just basic science that was done hundreds of years ago that had not been called into question until the 70s or 80s when it started to really affect us. This is a really fun plot for me, so I know I'm at a sci-fi convention, but I thought as a scientist it was my duty to put at least one really horrible graph in my presentation, okay? If you've ever been to a scientific conference, every slide is like this, except the text is way smaller, the resolution's worse, everything's blown up way out of proportion, and I'd be speaking in technobabble, literal technobabble the whole time. But this is a very special plot to me, because when I was a teenager, okay, I was a teen in the mid-2000s, and this was a time of peak climate skepticism. No one was really doing anything about climate change. We were emitting at crazy rates. I feel like skepticism and kind of ignorance was dominating the conversation. And me, I've always wanted to be a scientist. And even at the time, I was like, is climate change real? Should I care about this? So I did some Googling, the little scientifically curious kid that I was, and I found this plot. And I was like, oh my God. It's so clear to me now, okay? So what we're looking at here, before I even knew what Earth observation was, this is the first time I had ever really studied Earth observation data. And this is coming from the NASA IRIS instrument, another spectrometer. And what it was doing, okay, what it was doing is it was measuring radiation leaving our planet over the course of 30 years or so. And what this plot shows is the radiation leaving our planet in 1997 subtracted from the radiation leaving our planet in 1970. And you can see there's a very clear difference in the signature of the radiation, exactly where methane and carbon dioxide lie. What you're looking at in this plot is our planet literally heating up in front of your eyes. The radiation associated with carbon dioxide and methane can't leave our planet. It's trapped in our atmosphere, and it's heating us up between 1970 and 1997. It's only continued since then. If that's a little too abstract for you, or you don't get excited about spectroscopy in the same way, there's another planet where we've been measuring the climate over a really long period of time, okay? The Viking orbiter first arrived at Mars in 1976, and we've been measuring the changes in temperature at Mars for 40 years now. 40 years? Yeah, 40 years now, thank you. From Viking through MGS to Mars Reconnaissance Orbiter, there has been no observed trend in Mars climate change, okay? We're not seeing the same linear increase that we're seeing on Earth. And in the same time, the rate of Earth's warming has doubled since 1975, okay? So if someone comes at you and they're like, oh, it's the sun that's warming our planet, and this is totally normal, it's like, then why isn't Mars warming up? You know? And this is supported by our direct measurements of radiation leaving the sun and coming at Earth over the same time period. There's been no increase or trend in the radiation coming at us from the sun in that time. So it's just complete garbage, anyone that says otherwise. Whew. So this is the hardest part of the whole talk, okay? I'm gonna talk about where we're headed, okay, what the projections say, what the models say based on the kinds of emissions we're looking at right now. So if we hit 1.5 degrees warming, which is the most optimistic case, we're currently at 1 degree Celsius warming, and the hope is that we can keep it below 1.5 degrees. Current estimates put the likelihood of that happening around 1%. So if we're lucky and we do a really good job reducing emissions and we only hit 1.5 degrees warming, by 2040 there will only be 10 million people displaced by sea level rise. Not so bad, right? Only 10 million people. 99% of our coral reefs will be lost, but the 1% left will be a really great tourist attraction. Okay? So if we manage to keep it below 2 degrees, which is like a 5% chance of happening, if we really, we do a good job, not a great job, but a pretty good job of reducing our emissions. We're looking at the global GDP reducing by 13% by 2040, which, God, what's that, 20 years from now? 20 years from now, we'll have a 13% reduction in GDP despite our increases in population. 400 million people will be in water-threatened zones. What that means is places like Chile, where they're suffering extreme drought. Chile is already investing huge amounts of money into water desalination because they're really concerned about their nationwide water supply for good reason. So we're looking at 400 million people in that same situation. And the number of extreme heat waves we see is going to increase 32 times, okay? 20 years from now. 3 degrees, so this is more or less if we keep reducing emissions at roughly the same rate, maybe a little bit better. We're not doing a good job. We're not doing a terrible job. Kind of like middle of the line projections by 2100, so I guess my kids' time, maybe some of your grandkids' time, Southern Europe is going to be on a permanent drought. It's projected. The average Northern African drought will last 5 years at a time. And the areas lost to wildfires, so this is compared, I guess, to current day measurements, will increase by 2 times in the Mediterranean and by 6 times in the United States. Okay, this is the last one, I promise. This is if we kind of do business as usual and stop trying. We're looking at having half the current grain yield by 2100 that we produce today. And we'll have to support the projected population that we have in 2100, so obviously this will be a huge issue. And it's a projected GDP reduction by 30%. Okay, that's the worst of it. The worst part's over, okay? It's kind of like ripping off a Band-Aid if there's, instead of a wound, you have the end of the world underneath it. So what do we do? What do we do? Well, the IPCC, so the Intergovernmental Panel, not planet, if only, the panel on climate change has been very kind as to offer us a whole bunch of different pathways, a whole bunch of different solutions, a whole series of wonderful ideas as to how we could reduce our emissions and hit the targets that we need to hit in order to prevent the worst from happening. So they have 4 main pathways in the latest released report. I'm not going to go through each one of them in detail, but they do have some commonalities between them. One, obviously, we need to reduce our demand. We need to reduce our consumption of fossil fuels and stop emitting so many greenhouse gases. We need to increase efficiency in industry and transportation where possible. We need to revolutionize the way that we get our energy. Obviously, fossil fuels will have to be phased out nearly completely, and incorporate climate justice as much as possible. So, starting with some very specific targets, and I'm so impressed with this report, and I feel like if you're curious at all about climate change, you should go and read the IPCC summary for policymakers. I feel like a lot of the conversations I've had about climate change could be solved or moved forward very quickly if people had read this report. And yeah, here's one very specific target. So currently we have 5% or so electric vehicles on the road. We need to increase that to 50% or so by 2050. Raise your hand if that feels possible. I feel like that feels very possible, personally. I mean, given changes in technology, and as these technologies get cheaper, I really feel like 50% electric by 2050 is pretty feasible. Okay, so buildings, offices and houses, community centers, we need to reduce the energy demand in these buildings by 55 to 75%. This is for 1.5 degree warming. If we decide we're okay with 2 degree warming, it's more like 50 to 70%. So if you can imagine ways that your office could reduce energy by 50%, I feel like this is not a crazy target that we need to hit, given we have 30 years to reach it. I'm feeling pretty good. Okay, this is looking all right. Renewables, we need 70 to 85% of our energy to come from renewables. I feel like a lot of countries are close to this already. I know where I'm from originally, in Ontario, we're already there. I know there's a lot of countries in Europe that are moving very rapidly towards these targets. This is another one I feel pretty optimistic about if we keep the momentum going forward. Land use. So here on the right, I have a beautiful Sentinel-2 mosaic of some irrigation fields in Saudi Arabia. It's false color, they're not actually red. But if you've ever flown over these sort of circular crop rings, those are irrigation fields with a little sprinkler in the middle that kind of projects the water around in a circle. And as it is currently, I learned that we use 37% of our land on Earth for agriculture. And if you look at only the places where humans can live, so our habitable lands, that moves up to 50%. So half the land we have is currently used on agriculture. 77% of that land, the agricultural land, is used for livestock. Despite it, that's a hugely disproportionate amount compared to humanity's energy consumption. We don't get most of our calories from livestock, certainly not 50 or 77%. And the IPCC states that we need to reduce this to 60%. So if you are currently a meat eater, you don't have to totally stop eating meat, but maybe learn how to cook your favorite vegetarian thing and do that sometimes. This is the kind of progress we're looking at. But then this one, when I read this one, I was like, oh, gee. So I need to turn off my lights half the time and eat less meat, but industry needs to cut down their emissions by 90%. It's almost like most of our fossil fuels have been coming from industry the whole time. This one is very ambitious, and I'm not the expert on how we're going to be able to do this, right? When I look at these numbers, all I can think is we need a revolution in how industry does anything. And it's going to involve an almost complete emission of fossil fuels from industry down the road. Something that a lot of people don't know about our projections for climate change is that almost all of them require huge amounts of carbon capture and carbon removal from our atmosphere. Certainly all the ones that people are considering actually taking. We need to find a way to make our carbon emissions not only net zero, but negative year on year if we want to hit these 2-degree, 3-degree targets. All of them incorporate carbon capture in a huge way from our future projections to mitigate the most disastrous effects of climate change. And the scary thing about this is that while we have some idea how we're going to do this, there's not currently a solution. Okay, carbon capture technology is getting cheaper, but there's a lot of prototypes, a lot of studies, a lot of ideas, but nothing has really moved forward just yet. I saw an article the other day saying we have the potential to make carbon capture technology from $600 a ton to $100 a ton. I'm like, okay, why aren't we doing it yet? And I don't know, but what I do know is that we don't currently have a way to do widespread carbon capture implementation. But it's absolutely necessary in the decades to come. One figure I remember is that we need to reduce our carbon emissions by 80% by 2030. In total, in sum, so between all these targets. And on the projection we're at right now, I really don't feel like that's possible. Carbon capture is going to become critically important, despite us not really knowing how exactly we're going to do it. So in the theoretical case that we get really good at this and we start implementing it everywhere, it will allow us to get 8% of our energy from natural gas. In this fantasy scenario where we capture all of the carbon, we leave all the other fossil fuels in the ground, we stop using coal entirely, then we will be permitted 8% natural gas. This is one that worries me personally. So, some of those targets are easier to hit than others, right? And when it comes to climate change, I have good days and bad days, personally. When I first started researching this talk, I thought that there's no way I was going to feel optimistic about climate change by the end of it. But the more I researched and the more I started actually doing something, the better I started to feel. The IPCC offers no shortage of solutions. We have a lot of ideas, and we know exactly what targets we need to hit going forward, and a lot of them are actually very achievable. Here is a list of cities that have committed to going either carbon neutral or drastically reduced carbon by a given date. We have Boulder 2050, we have Copenhagen 2025, Oslo 2030. Raise your hand if you are from one of these places or live in one of these places, have been to one of these places. Great. Raise your hand if you're not from one of these places. We have a lot of work to do. We have a lot of work to do. Here's another plot, which, while not hugely encouraging, does offer some glimmers of hope, okay? So this is a plot showing the country-by-country emissions of carbon dioxide over the past 50 years. And you'll see, like, from sort of 1990 to 2015, there's a real story there. We see in 2000 a huge peak in the emissions from developing countries such as India and China. We see in 2008 that little dip there from the global recession, economic crisis. And then after that, from 2010 forwards, we see in developing countries a reduction year on year of emissions. We see in other developing countries it's plateauing. In developed countries it's reducing. In developing countries it's plateauing. The conversations we're having, the policies we're implementing, the technologies we're developing are having an impact, okay? We're not emitting more and more year on year. It's plateauing. It's drawing back. Things are moving, okay? They're not moving fast enough, but they're moving. And if we can keep this momentum going forward, it's possible we could hit the targets we need to hit by 2030, 2040, at least 2050 and beyond. While this is happening, there is more social momentum and there's more people showing up for climate change topics than I remember happening in my lifetime. Students are striking every week all over the globe. They've invited adults to join them, if you haven't heard of the global climate strike on September 20th this year. There's a lot more political will for changes and hitting these climate change targets now than there ever has been. Okay, but is it enough? Is this plateauing enough? Is this social momentum enough? I feel like it can be. So moving forward, like, what can we do as individuals, right? We've talked about what we need to do as nations. We've talked about what's happening on Earth. We've talked about what's happening socially. I like to think a lot about local action, right? I feel like if you start individually, if you start making better choices for yourself and then build outwards, maybe you talk to your friends, maybe you get vegetarian options at your cafeteria at work or in your school. You build outwards, start with yourself, and then grow and grow, join a local movement, start some form of activism. I feel like whatever helps at this point. Something I've seen a lot in the, more climate activist and to some extent the climate scientist community is people spending a lot of energy, emotional energy, intellectual energy, talking and debating about different solutions. Some people are like, well, individual choices don't matter, and other people are like, actually they do. And other people say we should focus on communal solutions, and it's just a huge mess. At this point, I feel like we're past the point where we need to be discussing solutions, we need to be implementing solutions. And anything that helps at this point helps, okay? I know when I think about climate change, I sometimes have this deep sense of hopelessness. I feel like it's out of my control. And I think a lot of us have learned to feel that way because it's something the public has been increasingly concerned about while leadership continues failing to respond to the crisis. And I don't think it has to be that way. I think we, as the public, have the power to hold our leadership accountable. There's been a massive failure in leadership globally when it comes to the climate crisis, and we need to get to the point where leaders step up and take action. And we can do that by holding them to these specific targets that we are now educated about. We need to make climate change an election issue every election. Every single party needs to have a climate change solution. It's not something that some people can be talking about sometimes. It's something that needs to be a dominant force in the conversation every time. Whew. Okay, so ending now. I thought I'd end on an Einstein quote, despite it being a little bit cliche. I was like, you know what, this has really been stuck in my head lately. And some of you may be aware that there are a lot of misattributed and like completely fabricated Einstein quotes. There's over 10,000 words of it on Wikipedia. I promise I checked. Albert Einstein definitely said this, and it's really been in my mind a lot lately. So I'm really grateful that so many people showed up for this talk on a Sunday evening. I was told when I was building this, like, am I really allowed to be political? Like, I thought this was supposed to be a science thing, and Thomas was like, you can have some teeth. I'm like, okay. I'll bring what I got. So thank you again, Thomas. Please join me back up on the stage.
And big thank you to Cassie.
Okay.
Very good.
It's so warm. Oh my, thank you.
So thank you very much to Cassie, and thank you to all of you for that reaction.
No one ever does that for science.
Yeah. We thought we just thoroughly depressed you on a Sunday evening. But we've got a few minutes now, and we're also at our stand again all day tomorrow, so if you want to have a more in-depth talk with us, then you can come by. You can also come and see what ESA Earth observation data can do for you, how you can get hold of the data, how you can start looking into this yourself, because I mean, the enemy of the people that say that these things aren't true is data, and you saw a lot of it from Cassie today, and we have a lot more that you can look at via our website, via our apps, and things like that. But right now, we're very happy if one or two people have some questions and would like to come up to the microphone that's right in the middle here, then go ahead.
Hi.
Hello.
My name is Lennart. Thanks for your talk. Wouldn't you prefer hydrogen technology over batteries, which are made of lithium? Because our lithium supply, our worldwide lithium supply is definitely limited, and we don't even have enough lithium for all the cars, to replace all the cars in Germany alone. So how are we going to solve this?
Well, I'm not a battery expert, but it sounds like you know a lot.
A little bit.
Yeah.
I mean, I know a bit more about batteries, but not so much about lithium supplies, which is a problem. I mean, no, we are aware of it, and I think battery technology developing is a critical area of research. We use it even for our spacecraft, not necessarily because lithium's running out, but because we know that just because we've got a good battery doesn't mean we can't find a better one. So we're constantly looking both within our agency and many, many researchers around the world at different battery chemistries that could potentially provide the next battery for the future. Hydrogen is very effective. You can store a lot of energy with hydrogen, which is very good. The only problem is that storing and transporting hydrogen can be challenging. So it's not impossible like all of these solutions, but as Cassie said, at this point we need to look for every solution we can. So we're past the point of this or that, and we're already on to the point of we try every solution, and anything that works we keep on going with. But yeah.
We could also get a gaggle of belters to find us some lithium from the belt or something.
Okay, thanks.
Hi, I really loved your talk. It was really motivational and all of that. And yay, science.
Yeah.
I mean, FedCon talking about science is really, really awesome, and especially that they're talking about climate change. And I was wondering, do you have a resource or a way of sharing like your awesome, awesome presentation to other people who can't be in this room, or the people who maybe missed the beginning of your talk? Is there a resource that we can use and share?
Yeah, that's a great idea. I could throw them up on Google Slides and share it, maybe.
Yeah, and there's also a great
ESA.
website from ESA called cci.esa.int. And there's an app you can get if you've got a tablet, which is a really nice app that you can play with. It's got videos about climate change. It's got lots more data and cool animations. In fact, some of the ones for this presentation were nabbed from that resource. So it's well worth looking through, and something to have a look through on a Sunday afternoon if you want to be depressed again. You can take a look at some climate change data.
Awesome, thank you.
Yeah, but if you specifically are interested, just throw me your email, and I'll make sure it gets to you.
Okay, cool, thank you.
One question about the organization of ESA and the missions that you run to monitor Earth. Seeing as they are often international and highly complex, can you give us just a brief glimpse on how prioritization works, how the funding is organized, and just what hierarchies exist or sometimes maybe limit you in what you do?
Yeah, that's a Thomas question.
No problem. Yeah, no, we've actually got two big families of missions. Cassie talked about the Sentinels, and those are missions that are done with the European Commission. So the European Commission work with ESA for us to deliver what we call the space segment of the Copernicus program, but all these cool satellites that produce this data. The theme there is to produce the very best Earth observation data that's the most up-to-date that's ever been produced, but for it to be free and open to all. So we don't hide it, we don't charge for it, you can do what you want with it, you can get the data. Prioritization there is driven largely by the European Commission, so they know what the hot topics are, and in fact Sentinel-7, the one that was not on that slide because it's the next mission which we're aiming for in 2024, is going to be a carbon monitoring mission. So it will monitor anthropogenic carbon, so that's human carbon emissions, with very small grids, so we can see, for example, individual factories or power plants, and it'll produce constant maps of carbon production all over the Earth. So that doesn't let anybody hide from the emissions they're producing, because it's not only governments or us that see that data, everyone will have access to it immediately and can cross-check and verify everything themselves. But that's the Sentinel program. They're looking at monitoring operationally. We also have the Explorers. And the Earth Explorers are missions that are answering new science questions about our planet. We've got a model of cryosat at our stand, which was answering the question, what's happening to our ice sheets? The spoiler alert is that they're not staying for very long. As you saw in the video, they're disappearing. But the Earth Explorers, there we put out calls to scientists, Earth scientists from around Europe and the world, to see to them, what are the biggest scientific questions that we could try and answer with space? Where can we try and make the most impact? And that's how those get selected at the moment.
Thank you so much.
Hello. I've got a question, something I heard about, that there's not only the influence of us humans on the climate, but there's also natural, climate change, that we've got ice ages and warmer ages, and how this influences our present situation, and whether it's supposed to be an ice age or something, or it's actually a warmer time, and it's warming up anyway right now. I'm not sure about that, but I heard something about it.
Yeah, it's very complicated, actually. Earth is a very complex system. But fortunately, we have a very good idea of what these cycles look like. You're talking about Milankovitch cycles. You're talking about the orbital parameters of our Earth and how close we are to the sun at any given time.
Something about that, yeah.
This is very well characterized, and it's very easy to piece apart the variables here. We're currently in an interglacial, right? We came out of an ice age. We're expecting another ice age in the future, or at least we were. It's very, very clear that we are experiencing an anomalous amount of warming given the solar cycles. As I mentioned near the start of the presentation, we directly measure the radiation coming from the sun to our planet, and there's no big upshoot like what we're seeing in the temperatures on Earth. It's more or less what we'd expect. So to say that there's some other natural cycle that's causing this huge trend in warming, that's a fabrication.
Yes.
Thank you.
Hi. Well, thank you for your talk. It makes us positive and depressive at the same time. And I think that the youth movement like Fridays for Future and the last European election showed that it is really becoming a topic that the people say, we need our leadership to do something. But you said everything about like CO2 reduction, but you also said that methane levels are rising. So would it also have a positive impact on climate change if we were able to reduce methane?
Yes, absolutely. Methane is a very powerful greenhouse gas.
Yeah. So like cut down on the livestock, which were like 70%, 77%
Yes,
of all
absolutely.
our
That would make a huge difference.
Okay.
Yeah, exactly. And in fact, carbon capture technologies aren't completely limited to carbon dioxide capture. We would also like to try and capture methane from the atmosphere. At the moment, we're going for the low-hanging fruit, which is carbon dioxide, which is easier to capture. And as Cassie already said, capturing that is pretty difficult, but it is an aim. I mean, as she said, and as you saw from the pathways there, we need to start scrubbing the atmosphere. It's no longer enough to just stop producing.
Thank you.
Hi, thanks for your talk. And I was wondering, in the beginning we had an image of the permafrost on the Earth, and I've read on the internet that inside...
Best source of information.
Yes, especially not particularly well-researched or true information, but yeah. Under or inside the permafrost, there's a lot of methane.
Oh God, yes. A lot. There's a lot of methane trapped in the permafrost.
And some people were saying that once the permafrost starts thawing, the released methane will trigger basically something that will catastrophically alter our climate due to the methane, and again, helping heating the planet, which will release more methane and so on until the point where no life is possible.
You're absolutely right. So what you're talking about is a kind of tipping point,
yes,
right? And we hear about these tipping points here and there when we're talking about the climate crisis. A video I almost included in this presentation is, it's this image over a permafrost lake bubbling. Literally bubbling continuously from all the methane being released from the permafrost beneath it. And as I've mentioned, methane is a very powerful greenhouse gas, and it's extremely hard to quantify just how much methane is trapped in the permafrost and what effect and when it's going to have on our climate system.
And methane is also an incredible flammable thing, so couldn't we just burn the entire thing? I mean...
To turn it into carbon dioxide or carbon monoxide?
Yeah, this is the problem.
Okay, thank you.
Thank you.
So, hi there. Nice talk, by the way. I'm totally with you about the responsibility that we have for climate change and for looking on our planet first, but at the same time, my question would be, what do you think about spaceflight pollution and orbital debris? So how can we take countermeasures? Because at the same time, when we're looking on our little planet, we should also take a bit of a look outside and take care that we don't forget about that within the next years.
Yes, absolutely.
Yeah, totally. I mean, I fly the Earth observation missions and we deal with it every day. I get woken up very early in the morning sometimes and get very grumpy into work to have to dodge out the way of some tiny fragment of space junk that's out there, because we've started using space like we're now using the Earth. We can start just chucking stuff away. Luckily, we're a bit further from catastrophe in space, and we're starting to make steps. So the UN, as well as recommending about climate change, is recommending what to do about space debris. We've now got UN guidelines that anything that we put into low Earth orbit has to return to the Earth's atmosphere within 25 years. And if we maintain that rate, we will keep space relatively clean. But what we need to start doing now is going and grabbing large bits of space debris, because we're already in a runaway effect. Just like our climate's in a runaway effect, space debris is a runaway effect. And not only is that terrible for polluting space, but it's also terrible because the things that it's polluting are the satellites that tell us all this telemetry about our Earth, and if we're to lose those, then we lose our eyes.
Yeah, and kind of bouncing off of that, you were talking about the carbon emissions that rockets themselves have, right? It costs a huge amount of fuel to send anything into space. And I think the philosophy that we're starting to take with space debris, this idea that if you put it up there, you're responsible for it, is something that we could introduce to these industries where some amount of carbon emissions are essential, right? Like the people who are polluting need to be responsible for the pollution that they created. They need to offset that somehow. So I think this philosophy, and this is something I was talking about at the booth earlier with a couple people, that we have of space debris, it's like you're responsible for your pollution isn't free, is something that we could introduce to fossil fuels going forward.
Thank you.
Thank you.
Thanks.
Thanks for your eye-opening and excellent presentation. You were talking about different levels of elevation you are measuring on our planet. And if I remember correctly, even on our oceans. From my experience in a bathtub, I actually thought that water is quite level and flat. And I find the idea that there are mountains of liquid water in our oceans that won't flush away quite counterintuitive. Could you elaborate on that?
Yeah, so the ocean actually isn't flat everywhere. It depends a lot on the local gravity underneath the column of water at that location.
And there's also temperature effects, which is what's causing it to bubble up. I mean, it's not quite like a kettle, but it's not far off. A lot of the heat that we're generating in our atmosphere at the moment is going into the oceans. The current estimates are about 4 Hiroshima bombs, 4 big atomic bombs of energy go into our oceans every second from the warming on our planet.
I didn't know that.
And you know what happens if you turn your kettle on? Not much happens at first. You sit around and wonder if it's actually switched on for the first 2 or 3 minutes, and then it starts to get really dramatic. And that's the situation we're in with our oceans at the moment.
Yeah, and on top of that, so my understanding of sea level rise is that while our ice sheets melting is contributing to that, a majority of the expansion is just thermal expansion from the oceans absorbing all of this energy.
Okay, thank you very much.
Thank you.
Hello. I heard something about if we pass that 1.5 degree limit, that we would fall into a spiral of the Earth always getting warmer and warmer. Well, you showed us some ways that the Earth could even get 4 degrees warmer. Does that mean, is it true that we can't stop global warming after that 1.5 limit?
Yeah, that's a very good question. So it's true that if we cut off all of our emissions tomorrow, even, the Earth is going to continue to warm for a while after because we still have all of this remnant carbon dioxide in our atmosphere that's continuing to trap heat, right, within our planet. The projections that say we're going to reduce warming or prevent warming from increasing all rely on carbon capture. We need to get our emissions negative. We need to extract that huge accumulation we have of carbon dioxide in our atmosphere if we want to hit these targets. So that's a very good question.
Thank you.
Okay, thank you very much. I think this will be the last question because I believe there's a film premiere on here after us. Very exciting and probably more happy than what we've been talking about. But we'll be around all of tomorrow and probably around this evening at some point. So if you've got questions, we can certainly continue the conversation, but please.
Hi. I'm interested in the solution you said, for example, the responsibility for everyone and the industry. Which part is, for example, the energy which you need, for example, data center or something like that? And because if you use your phone and, for example, your analytics and something like that, you need much more power and more. So.
Yeah, no, that's a very good point. In fact, at the moment, the majority of carbon emissions come from heavy industry, so not data centers, but they do generate a large amount of heat and use a large amount of energy. Now, if that energy is produced in a renewable way, that's already a big step. But in fact, most data centers, purely for money reasons, and at this point will take any reason they want to take, They use heat recovery systems. So these data centers generate vast amounts of heat, but you can recover that and turn it into energy or heating to use elsewhere. And that's what we need to be doing. For every drop of emission, every watt of electricity produced, we need to squeeze every last use out of it, because that's the only way we're going to start getting things back under control.
Okay, thank you.
Okay, thank you. So, thank you to everybody for listening. Thank you, Cassie.
Thank you.
And have a very good evening.
I dropped this like 3 times.
Vielen Dank, dass ihr euch das Video angesehen habt. Wenn es euch gefallen hat, dann lasst einen Daumen nach oben da. Hier habt ihr nun verschiedene Auswahlmöglichkeiten. Ihr könnt oben links unseren Kanal abonnieren. Oben rechts geht es weiter zu tollen Videos von diesem Event. Unten rechts gelangt ihr zur Internetseite vom nächsten Event. Zu guter Letzt kann ich euch noch den Space Store empfehlen. Hier gibt es alles Mögliche an Fanartikeln zu euren Lieblingsserien und Filmen. Bis demnächst auf diesem Kanal.